Okay, so back to the pedigree, and this is a pedigree representing an autosomal recessive trait. So the individuals who have the trait are shaded, and we know that their genotypes are little a because they have the disorder. And the disorder is defined as being a recessive disorder. So I wanted to point out the individuals in generation 3. So what does that double line represent? And what it represents is that the bottom line here that connects them represents that they had children together. But the top line represents that there is a very close genetic relationship between them, and that is that they would be first cousins because their moms are sisters. So with their moms being sisters, that makes them first cousins. And this is what you see happen a lot of times when two very closely related individuals have children and there is the history of a recessive disorder in their family, then you tend to see it in the children more often. So, so that's what we're looking at here. I also want to point out to you some of the individuals that maybe, let's see. We know that in generation 1 that the original dad, that there's no way to be sure of what his genotype is. And also in generation 2, the fathers, we can't see enough to know what their genotypes are. But we know that the parents in generation 3, this individual and this one, this one, we know that these parents are big A, little a, because both of them had to have a little a in order for their offspring to be recessive, to have two little a's. So those are some things I wanted to point out about that pedigree. And then this is information on some of the more common autosomal recessive disorders. It says if both parents carry one copy of a recessive gene, they are unaffected. We just call them carriers. But they're capable of having a child with two copies of the gene. Methemoglobinemia is a relatively harmless disorder. It's accumulation of methemoglobin in the blood, and it causes the skin to appear bluish purple. And that's going to look like this. Do you see the nails? The skin has a bluish purple appearance to it in comparison to the hand on the left side of the page. But a recessive disorder that is very harmful, does have serious consequences, is cystic fibrosis. Cystic fibrosis causes mucus to build up in the bronchial tubes, the airways, and also in the pancreatic ducts. And that mucus is really thick and viscous. And it's caused by a faulty chloride ion channel. It keeps chloride ions and water trapped inside the cell. And so what would have to happen normally is chloride ions would have to leave the cell for the water to follow. And the only way to loosen up the mucus that's outside of the cells in the airways is for water to mix with that mucus. So without the water, with the water not being able to leave the cells, the mucus becomes very thick, and it causes breathing problems. It also causes problems with the pancreas as well. Now, those are two autosomal recessive disorders, but there also are autosomal dominant disorders. One of them is called osteogenesis imperfecta. Gosh, I can't think of that movie right now, but there's a movie starring Samuel Jackson, and he plays a guy that has this. His bones break easily. It's something like glass or something like that. Hold on. Okay, I'm so sorry. It's the Samuel Jackson movie is called Unbreakable. So if you ever want to watch it, but it's a good movie. But he has this condition, osteogenesis imperfecta, which is a dominant disorder. It's characterized by weakened, brittle bones. Most of the time it's caused by mutation in the genes required for the synthesis of type 1 collagen, which is found in our bones. But all you have to have is one dominant allele to get this. You might ask yourself why it is that we don't have a whole lot of people with this disorder. Most of them don't reproduce. So this disorder is so bad that they can actually die early, die young, and even if they don't, they're not likely to have children. Okay, they can have children, but they just aren't likely to have children. So a dominant disorder is characterized by two parents having a dominant disorder. So the two parents would actually have to have the disorder, and so they would know they have it when they have children. If they both are heterozygous, it would be possible for them to have an unaffected child. They could have a child who's recessive, because they both have a copy of the recessive allele. But anyway, one of these dominant disorders is osteogenesis imperfecta. Another is Huntington disease, which is a neurological disease that leads to progressive degeneration of brain cells. This is a disease that doesn't appear until the person is middle-aged. So a lot of times they've already had children. And then there is hereditary spherocytosis, in which the red blood cells become spherical, much more rounded. They're already rounded, but they're flattened. They're kind of flattened on the top and bottom of the red blood cell. So they become round like a ball, and they're fragile and burst easily. So this is also a dominant disorder. And you can see a pedigree showing a dominant disorder. If you've got two parents who have the disorder, having children, if the children have the disorder, we know they have at least one big A. And then if they have two children who are unaffected, then we know the parents are carriers. We know they have one little a each because they have children who are little a, little a. Just looking at the overall pedigree, though, there are a lot more individuals with the disorder than in the recessive pedigree. And that's a kind of a little hint that the disorder is dominant rather than recessive, because dominant disorders are going to affect more individuals. Do notice that the parents in generation 2 that are both unaffected, all their children will be unaffected because being unaffected is recessive. They don't have any big A's to give. Now, beyond Mendelian inheritance, so these are, what we've looked at so far has been called simple dominance. That means that every trait that we've looked at has a version of the trait or an allele that is dominant and an allele that is recessive. But there are other inheritance patterns. So one of these is called multiple alleles, and that means that there's more than two alleles for the trait. ABO blood types are an example. There are 3 alleles for the ABO blood type. Now, people are still only going to inherit 2 alleles because they only have 2 parents. But there's 3 versions. There's the IA, the IB, and the little I. So if you inherit, let's see if there's a chart. Yes, if you inherit IA or IA little I, then you're going to be type A, have type A blood type. If you inherit IB from both your parents, or if you get IB from one parent and little I from the other parent, you're going to get type B blood type. Now, in order to have type AB blood type, you got to have IA from one parent and IB from the other. And then, like, for example, my blood type is type A. My daughter's blood type is AB. So her father must be at least type B or type AB. He must be one of these where he could have given her that IB allele. I gave her the IA, but her father would have had to have given her the IB. And type O is genotype little I, little I. So you can see there's 3 possible alleles. There's IA, there's little I, and there's IB. But you're still going to get 2 of each. I mean, you're going to get two alleles for the trait. Sometimes they're the same, sometimes they're different, and those combinations of alleles are going to tell you what your blood type is. So blood types, ABO blood types exhibit multiple alleles. They also, ABO blood type also exhibits codominance, and that is exhibited in blood type AB, because the IA allele and the IB allele are equally expressed. What happens is a red blood cell for a person who's type AB, let's say this is their red blood cell, they're going to have A antigens on the surface of their red blood cell, and that comes from the IA allele. They're also going to have B antigens on the surface. That means both alleles are expressed. That is codominance. Then we can have something called incomplete dominance, and this is close, very similar to the blending hypothesis. The individual who is heterozygous actually has a blended or an intermediate phenotype between the two homozygous individuals. We have flowers called snapdragons, and when they're homozygous red, both alleles are red, then the flower color is red. When they're homozygous white, their flower color is white. But if they have a red allele and a white allele, then they're going to be pink. And that's an example of incomplete dominance. And here's I didn't even have to do all that. R1 stands for red and R2 stands for white. So if you get R1 and R2, the flowers are pink. This shows you a cross between two pink flowered snapdragons. You get a 25% chance that the flowers will be red, a 50% chance they'll be pink, and then a 25% chance they'll be white. Another incomplete dominance example is familial hypercholesterolemia, which is genetic high cholesterol. If they're homozygous for FH, then they're going to develop fatty deposits in the skin and tendons, and they may have heart attacks during childhood. So it has nothing to do with diet. If they're heterozygous, they may suffer heart attacks during early adulthood. But if they're homozygous, they will not have high cholesterol, at least not genetically. They may have it because of their diet later on in life, but they're not going to have it as a young child. Now, another type of inheritance is incomplete penetrance. This is when we don't have the expression that you would think based on the alleles that are inherited, that they're not expressed the way they're supposed to be. So the dominant allele may not always lead to the dominant phenotype in a heterozygote. Okay, one example of this is polydactyly. Polydactyly means there are extra digits on the hands, on the feet, or both. So you have either extra fingers, or extra toes, or both. That is a dominant condition. But not all individuals who inherit the dominant polydactyly allele will exhibit the trait. I mean, you don't see a whole lot of people who have extra digits. And that is because of incomplete penetrance, because it is a dominant disorder. Okay, pleiotropy is when one single gene, causes many, many different traits. And Marfan syndrome is a disorder that exhibits pleiotropy. So in Marfan syndrome, the individual has disproportionately long arms, legs, hands, and feet, a weakened aorta, and poor eyesight. The tissue defects are within connective tissue, so it affects the skeleton, the heart and the blood vessels, the eyes, the lungs, the skin. I'm thinking there was a picture of someone with Marfan syndrome, but we don't have one. But anyway, that's an example of pleiotropy. That's when a single gene affects different traits, many different traits. And we also have polygenic inheritance, which is the way that we inherit skin color, our height, our eye color. If you think about these traits, there's not 2 versions or even 3 versions. There's many